off at this example, right? So we started working on the example, and we stopped midway. So we'll wrap that up and then move to chapter 2. So I think where we stopped was, again, we said that we want to relate V output to Vs. That's the objective of what we're trying to do all along. So we have a sensor input. We want to move that sensor input to some computer at the end of the day. So I would like to put an amplifier here because I do not want to draw power from the sensor there. So I want to figure out how to relate V output to Vs. So we related, V output and micro Vi, right, using a voltage divider rule. And we related, so Vi here is basically this voltage here. And this voltage here is related to Vs by this voltage divider. That's what we did yesterday. And today we will just, put it in a certain nice format to make it easier for us to understand, or relate it to the single time constant circuit that we talked about, right? So since we only have one capacitor here, this is basically a single time constant circuit. So a single time constant circuit will always behave like the low pass or high pass filter that we talked about. So the behavior will be exactly the same. So the frequency domain plot will be exactly the same. The phase domain, the frequency domain plot of the magnitude and the frequency domain plot of the phase of the transfer function will always be the same. It's just that where are the numbers, right? Where is this? Where will be the corner frequency? Where will the magnitude be at DC, etc., etc. So, so if we go back and look at these plots, so this was the table I was referring to yesterday. So we derived these relationships for the low pass filter configuration, except that we had our k here. They generalized it to a constant k as the magnitude. In the pure low pass filter, where you just have one R and one C, this k happened to be 1. When we derived the equation last time, the k happened to be 1, right? So, but in general, it can be k. In general, we can have a magnitude. So this general condition is what we see in this circuit that we're analyzing today. Because it's not a simple R1, R1C, then we have some gain. And we will go through that. We will look at how we will utilize that. Okay, so this is the objective, right? So since we have one C, it's obvious, and this C actually is also in parallel, right? So if you see here, this capacitor is in parallel, right? If we go look at the amplifier model that we're playing with now, the capacitor is also in parallel, right? So it tells you something. It tells you that it's going to be similar probably to the low-pass filter, right? But we are deriving the exact relationship in the example between V output and Vs. So we started off by saying that the Vi here is related to the sensor input by this voltage divider. So Vi is equal to Vs times Zi over Zi plus Rs, right? So we found this relationship. Then we moved this Vi to the next stage here, and we related this mu Vi to V output using this voltage divider. That's what we did last time and where we stopped. And so they go through that, and for convenience we utilized admittance. So we know that Zi is the parallel combination of this Ri and Ci. To add two impedances in parallel, 1 over Z equivalent of two components in parallel is 1 over Z1 plus 1 over Z2. So you can add those, and then you can, instead of representing them as impedances, it's nice to just flip that and represent that as an admittance. That's what we said. We discussed that last time. So we divided by what? What did we do? We divide by Zi. Right? We said if we divide by Zi, so if I divide this top and bottom by Zi, I end up with a 1 here. So divide by Zi, divide by Zi, I'm left with a 1 here, and then 1 plus Rs divided by Zi, which is Yi, right? So 1 divided by Zi is equal to Yi, and that's what we have here. Okay, we're fine with that. And then what is this Yi? This Yi is basically the admittance of the Ri in parallel with Ci. right? So it's this admittance of this parallel branch. This admittance of this parallel branch is basically 1 over Ri plus SCI. That's this parallel admittance here. Then what? Then we do some more simplification. So then we brought, so this is Vi, we bring Vs to the denominator, so we calculate Vi over Vs here. So we have our Vi over Vs equal to some term. Yes, ma'am.
All of this is to get T
No, all of this is what they're asking for in the problem is I am putting this signal, point V1, is point, this is your sensor. The sensor is giving a signal of 0.1 sine 10 squared t. The sensor is giving this data for some physical condition. What is this data going to look like if you pass it through this amplifier? That's the problem. Okay? Sorry, maybe I didn't just elaborate on that. But I didn't read. I didn't read the problem. But this is the objective, right? You have sensor here giving some data. This data is in the form of 0.1 sine 10 squared. So omega here is 10 squared. Omega here is 10 to the 5th, omega here is 10 to the 6th, omega here is 10 to the 8th. So they're changing the frequency of the input signal. The sensor's frequency is changing because it's sensing, it's converting light to frequency, right? It's converting light to a frequency of a sine wave, for example, yeah. So they're telling you, okay, what is this going to look like at the output of this system? So for you to understand how it's going to look like at the output of this amplifier, you have to find the relationship between Vs and V output. So we're trying to find that relation. How do you find that relationship? By finding, okay, a relationship between V output and this dependent source. This dependent source is basically controlled by this Vi. This Vi with respect to Vs are related by this voltage divider. So, and we will now relate V output to Vs using a transfer function. That is time dependent because I have a capacitor in there. Right, so I have J omega C because I have the impedance of the capacitor. Right, so anytime I have the impedance of the capacitor in there, so I have some time dependence. So how many time dependent variables, elements do I have in the circuit? 1. So my objective would be to take this, fine, we're starting to derive these relationships between the voltages. I want to make sure that, so this is Vi over Vs. So this is Vi here over Vs. I want to now relate Vs and V output. So I will manipulate this a little bit more using the voltage divider at the output. And then I want to do what? I want to be able to put it in a format that is easy for me to plot. I want to put it in this format. I want to make sure that at the end I put the transfer function in this format. I have a gain on top, and then 1 plus S divided by the circuit time constant. Remember omega naught is equal to 1 over tau. Tau is equal to RC or CR. Yes? No? Am I confusing you? You're good? Okay, so it's just going to be manipulation. What we did now is really we can stop. Okay, just to make things easy. So we found Vi over Vs. How do I find V output over Vs? I know that V output and over Vs are related by. Okay, so before doing that, they want to clean the format a little bit. So Vi over Vs is in this format. They want to make it closer to this constant over 1 plus S divided by something format. So what they did was they factored 1 over 1 plus Rs over Ri out in the previous expression, and they ended up with what? 1 over 1 plus Sc times something, right? So in the low pass filter, it was 1 over 1 plus Sc times R, right? Where C times R was the time constant, right? So this is going to tell us that this is going to be the time constant of the circuit now. This R here, this combination of Rs, Ri, Rs plus Ri, is an indication of the time constant of the circuit. That multiplied by C is an indication of the time constant of the circuit. Right? Before, in the single time constant circuit, it was 1C times 1R. Here, we have a lot more R's. What are these other R's doing to the circuit? They're obviously changing the time constant, right? The time constant depends on the values of the R's and the value of the C's that you have in the circuit. So now I have many different more R's and I have 1C. So this 1C had appeared here, when I just manipulated this expression that I derived from the voltage divider rules, and I ended up with something fine, closer to what I would like to reach. This one, or this k over 1 plus s times, or divided by some omega naught. Okay? So I want to reach, let me write it here.
Do you have something in the exam? Like saying,
Yeah, equation sheets, yes. You will have, of course, this is like the core of this chapter. So we want to reach something that looks like what? K over 1 plus S over omega naught. Omega naught?
Just C over omega naught.
Omega naught is 1 over RC. Right? So it's 1 plus S C times R. That's the format I would like to reach.
Oh.
Right? So this looks like that. Where this is what? This looks more like the gain K now, part of the gain K, because now I still have VI over VS. I don't have V output over VS. V output over VS. That's my objective. But I know that V output and VI can be related by this voltage divider rule at the output of the circuit, right? VI and V output, I can relate them now. So I will. That's the next step, is to relate, to relate VI and V output by the voltage divider rule. So what is V output equal to? V output is equal to the dependent source voltage multiplied by RL over RL plus R output. So it's basically this combination, these two resistors here. So V output is equal to mu VI times RL over RL plus R output. Right? So I related now V output and VI. So now I can take, I want to remove VI from this equation, right? So I solve for VI and substitute up here. In that case, I will get a relationship between V output and VS. And which is my objective? That is the objective that you want to reach. V output and sensor input, which is now, we're going to start playing with the sensor input. I will put different data at the sensor input and see what we get at the output. So this is the relationship that will relate those. So I took this, substituted for VI here, and found the relationship between V output and VS. And algebraically, I manipulated it such that what? Such that I have a constant K. So this is all of this is now K. All of this is now constant K. So this is now like the K in the table. So K over 1 plus S over omega naught. This is K, right? And then 1 over 1 plus S, all of this, right? So C 1 over CI, all of these resistors is omega naught. Okay? So I put it in this format because I know that I don't need to now come up with a new plot every time. I can just utilize the same plot that they've given me. I don't need to go and plot it every time. It's the same plot that I can utilize to find values.
So it's like a proof, and we just use the formula and then.
Yeah, you're trying to fit your circuit to that. Actually, you don't need to do that. If you don't want to do that, you don't need to. You can plug here numbers and just find, this will be a number on top and a complex number on the bottom. Find the like we did last time. Find the magnitude for the top and magnitude for the bottom, and this is the gain of the circuit, the voltage gain of the circuit. Find the phase of the top, find the phase of the bottom, subtract them from each other, and this will be the phase output. You can do that. You can do it that way if you don't want to do the algebraic simplifications. But if you do the algebraic simplification such that you put it in the format that is something we know beforehand, then you don't have to plot. You don't have to worry about how the plot will look like, because you know that the plot will look like these things we have up here. The plot will look exactly like this. We know that the plot will look exactly like this. So this will be the magnitude, this will be the phase, this will be the frequency, and the magnitude is, and this is the magnitude divided by k. So that if you have, if k is equal to 1, then this is the magnitude. If k is equal to something, you put k, you plug your k in here, right? So So let's see what's gonna happen. So we can go that route. There's a trick, however, right? So we said that this is what we will what will resemble our k, and this is what will resemble our time constant
Omega naught.
tau. CR is what will resemble our time constant, which is fine. Omega naught is equal to
1 over
1 over tau, which is 1 over C times the combination of resistors that we have in here, right? So you went that route, right? That's one way to derive this relationship between V output and Vs. There's a smarter way to do it, right? There's a smarter, simpler way to do it, yeah. So we know that this is a single time constant circuit, right? So there's one approach to quickly come up, again, what do I want? I want to come up with my gain, and I want to come up with, is this gain frequency dependent?
Is the frequency all the same everywhere
What do you mean?
in the circuit?
Look at it. Don't answer me without looking at the, did you look at this?
It's not frequency dependent.
Okay, that's good. That's the question. That's the right answer, right? It's not frequency dependent, right? So if it's not frequency dependent, so maybe I can just put frequency equal to 0 and then eliminate my capacitor. It's an open circuit, and find the voltage gain like I did before, right? That's a smart way to do it, right? Then I found K, and then I have, what do I have left? 1 over S over omega naught, right? S is S. So so you found K easily using the, just resistor circuits like we did for the previous examples with only resistors, right? So K you can find that way because it's not dependent on frequency. So if the configuration of resistors is the same, okay, put frequency equal to 0. Frequency equal to 0 will give you the gain of this circuit, right? For steady state, for DC. So you found K that way. So you didn't have to derive K using all of this stuff we did in this example, right? So that's one way to do it, and include admittance and include capacitance. Because I'm lazy, I don't like to write S, C, blah, blah. So it's easier to find K the other way. So that's one approach. That's K. So here, this is done. Now, if I can find also omega naught,
This one time.
then it's wonderful, right? If I can find omega naught in a smart way, it's wonderful. So one smart way to find omega naught is to do this. Look at your circuit.
You just find tau.
How do you find tau?
You have capacitor. Yeah.
Oh, you used to do that? That's good. So the way a good way to, or easy way to do this is to stand and look at your capacitor, at the terminals of the capacitor, short any sources, and look at what resistors are in parallel with the capacitor, and that will be your circuit time constant. So what if I do this? If I'm holding this capacitor here, and I'm looking from the nodes of my capacitor here, looking into the circuit. Right? I short the source, and I look at what's the equivalent resistance in parallel or at these two nodes, like a Thevenin equivalent resistance between these two nodes. What is it? It's these two parallel RS times RI over RS plus RI. Right? So if that's the case, then what I'm claiming is now tau is going to be equal to Ci times the parallel combination of Ri.
The product of the sum.
No, these two are parallel. Ri,
The
Rs,
product of the sum.
Ri plus Rs. So this is your time constant. So omega naught is equal to 1 over time constant.
Is this method going to work all the time?
Yes. Yes, the trick works.
That's actually, I was like, why do you use omega naught when you can just find tau? That's something
It's the same.
Yeah.
Time constant of the circuit is related to the
like, why is it
natural
in the
frequency of the circuit, right?
form? No, in the form.
Omega naught is
Why
in
is
that.
it 1 over 1 plus S over omega naught rather than S tau? Because I feel S tau is more natural.
Yeah, but tau, fine. But you want to plot against frequency. Your frequency domain plot is against frequency. That's why you would like to maintain it as omega,
I see.
right? So you don't want to plot against time. You're plotting against frequency. So it's 1 over tau, right? But this way, you don't have to go through this mess. And it's a nice, easy way to do this. And they talk about that here in the textbook. So tau is now equal to the Ci times RIRS times over the sum of the Ri times Rs. So now I have what? Now I have the time constant. And the discussion I was talking about to find K. So if found K, they also talk about that here. Put S equals 0. S equals 0, what is going to happen to the capacitor? Capacitor is an open circuit. If it's an open circuit, do the same voltage, the gain work that we did last time with only resistors. No need to add the capacitance and admittance and S from the beginning. So do that to calculate K. And you will be able to calculate K that way. So if S is equal 0, this is K. So plug S is equal 0 from the beginning. From the very beginning, plug S equals 0, and then you will end up with K very quickly. Okay?
Do I choose that as equal 0?
Yeah, you plug in S equals 0, meaning what? Meaning that you remove the capacitor from the circuit. Right? That's what S equals 0, because capacitors for DC are open circuit. So basically, open circuit the capacitor, remove it from the circuit. And then you have the pure resistive circuit, and it's very easy to do the voltage relationship, because they're all going to be voltage divider rules, simple voltage divider rules without any capacitances and admittances and impedances, complex numbers, none of that stuff, right? So that's one way to do it. You can do it either way; it's up to you, right? So I recommend doing it the easy way. Because as soon as you find one capacitor, you do it that way. Okay, so then we found, so this is K, this is tau. So we found this information in two different ways. And then what does the problem ask for? The problem is asking for, okay, now calculate the values of the DC gain. Now they're going to plug in numbers for the values that you have. So they're going to, the transfer function that we calculated last time. Now you just plug in some numbers. So they're giving you RS, they're giving you RI, they're giving you CI, they're giving you the gain, they're giving you R output, they're giving you RL, and they're asking you to calculate K, the gain, and the tau, or omega naught. And they're asking you to calculate those values, and then they're asking you to look at, these are input signals that are coming from your sensor. How will they look at the output when you pass them through this amplifier? So let's look at that. So we took our equation for K here, and we substituted the values that they gave us. The result was 100 volts per volt. It's a gain. Remember, it's a gain, so it doesn't have units, dimensions. Yeah. So it's 100. And then this is the gain in absolute value. I would like to plot the gain in dB. So I will take 100, multiply, 20 log 100 is going to be equal to 40 dB. Right? So the gain that this circuit will provide is 40 dB. So the DC gain. So what does this mean? Sorry. We know it's going to look like this because it fits the low-pass filter K over 1 plus S or omega naught, right? Format. What is the value here? No, the DC gain. So they're telling you, so this is the low frequency gain, K is the DC gain, right? This is the gain of the circuit at DC. Not necessarily 0. Sometimes you want to amplify the voltage, right? If it's 0, it means 20 log 1. So meaning the V output over V input, or sorry, V output over Vs in this case is equal to 1, right? That means the signal is going through with no effect. You're not amplifying, attenuating the signal at all, right? So that's 20 log 1. But what if I want to amplify the signal's voltage magnitude? Then I don't want this to be 0. I want this to be something else. In this case, V output over V input is equal 100. So 100 in dB is 20 times log 100. That would be 40 dB, and that's what you have here, right? So that's the DC gain here. That's 40 dB. Okay? Okay with this or no? And where is this point? This is omega over omega naught equal 1. So omega equals omega naught is this point. This is whatever this frequency is, whatever. So now we need to calculate omega naught to be able to find this point, right? So we calculated omega naught, we know is equal to 1 over tau, and we were given Ci, Rs, and Ri, so we can calculate omega naught.
Isn't S equal to JW?
J omega, yes?
So at this point, basically, like, you know, when you take the complex, like there's a real part and then an imaginary part, right?
Yes, yes.
So this is just like.
Remember, this what we did was exactly like we did for the simple RC circuit. We have a transfer function.
Okay.
This transfer function, we will find its magnitude and we'll find its phase. Now what I'm doing is finding the magnitude. This magnitude will change from DC all the way to high frequency. Right? But we've simplified that. We know beforehand, since it fits this format of K over 1 plus S over omega naught, then we know that the plot will look something like this. We know that the magnitude plot will look like this. We know it will look like this, right? Yes, ma'am.
In some cases, it wouldn't fit the format.
No, with a single time constant, it will always fit. Either this low pass filter format or the high pass filter format.
If you have to
No, it will not fit. It will not fit.
And we can tell if it's a low pass or a high pass by the capacitor position.
Probably. Yes. Yes, you should be able to do that.
So that's something we should know.
So we know it's going to look like this. But what is the value here?
okay.
Yeah, what's the gain? The value here is the DC gain. Here they put it at 0 because of what? Because it was 1. Exactly. So 20. When we did it for the simple RC circuit, it was 1. But in general, it's not 1. In general, it's the DC gain. Whatever it is, that's the DC gain here. And then this point here is 1. 1. This 1 happens at what? 1 means omega is equal to omega naught. Right? So what is this omega naught? It's good to know what the omega naught is. So fine, you know that this is happening at omega over omega naught equal to 1. But it's good to know what omega naught is for your reference, because this is fine. This is frequency over frequency. So this is actually dimensionless, right? So, but if you want to plot against frequency, then you have to know what that frequency is. So you have to know what omega naught is, right? But automatically you know that it will fit this format. Automatically know that. You just don't know where this is. This is a DC gain. It happened to be 1 here because of the value of K was equal to 1 in the simple RC circuit. Okay. So since we now need to know omega naught, then we just calculate. We substitute with the values that they gave us for R and C, and we calculate omega naught. So we know that the natural frequency of the circuit is 10 to the 6 radians per second. Right? So now what? So this is this is in radians, and we can write this radians 2 pi f in hertz is equal to the value in radians. So frequency f naught, or the natural frequency of the circuit, is 159.2 kilohertz. This is the frequency where? Yes, this is the corner frequency of the circuit. This is the frequency that is corresponding to the minus 3 dB loss in magnitude. 1 over square root of 2. This will correspond to that. So if you substitute with that frequency, remember you have now a time transfer function that contains omega, right? This transfer function here contains S, j omega. If you substitute with f equal to 159 or omega equals 10 to the 6 radians, what will happen? Your magnitude will be minus 3 dB. You know that, right? Because you've calculated omega naught. You've calculated your corner frequency. This is the corner frequency of the circuit. Okay? Anybody confused? Confused? Ask.
I'm confused about how everything is like goes back to 1 over square root.
No, it doesn't go back to 1 over square root. It's just
a
a...
corner frequency.
Yeah, sure. So I want to plot it, right? I want to plot the magnitude. Again, all I want to do is plot magnitude of my transfer function. So I want to plot V output over Vs. I want to see what output I get when I have a certain sensor input. I want to do that versus frequency. And I want to see the effect of the amplifier on the phase shift of my transfer function. I would like to see if I put in this, what is the phase shift of V output over Vs? What is this phase shift going to be? If I put a certain Vs, what will the output look like? Is it going to be in phase with Vs, or is it going to be out of phase with Vs? So I want to plot the phase versus frequency. Right?
And we always plot in decibels.
And we will always plot the magnitude in decibels and the phase in degrees. Right? So, but omega naught happens to be an interesting point because I know that at omega naught, at omega is equal to omega naught, or F naught in this case, what's going to happen to the magnitude plot? I know that the magnitude plot will go from my DC gain, which is K. This is your DC gain in dB, right? At F equals F naught, the magnitude will go from your DC gain down 3 dB. We know that. So it's easy for me to plot. Okay, now I know this point is like this.
3 or minus 3?
It's 3 dB lower than your DC gain. Your DC gain here was 100 volts per volt. In dB it was 40 dB. So this is 40 dB, right? What is this? 37 dB, right? This point here is 37 dB. So then I can plot. I know that I can start at 40 dB, and I don't know how exactly it will look, but I know that at the 3 dB frequency, at my corner frequency F naught, it will go down 3 dB. How does it move from here to here? I'm approximating here. You have to plug in values and go and take. Okay, F is equal to, instead of 10 to the 6th, take 10 to the 5th, 10 to the 4th, 10 to blah blah blah. Take every single point and plot it, right? If you want to plot it in detail, right? But I don't care. I'm just going through and just plotting like that, just numerically, just an estimate. But they've given us a nice plot that is sort of normalized up there. This is sort of a normalized plot. This is a nice normalized plot for a single time constant circuit. Right? I know that this point, omega over omega naught, are equal. If I go up here and I measure here, this is, if you go, you don't need to know that this is the 3 dB frequency or whatever, right? So you can actually physically, measure it if you print this out and measure, and divide this up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, fine. If you divide it into 10 and go across this point here with a ruler, you will see that this is approximately 3 dB less than this point, approximately. So that's why this curve is a curve that you can utilize. But you will have to plug in your proper values. So plug in values for your circuit. In your circuit, your DC gain was 40 dB for the circuit that we came up with now. So what is this point? 37 dB. Where is this occurring? At F naught or omega naught, which is 10 to the 6 radian per second. Right? What is the slope of this? It's always going to be minus 20 dB per decade. So every multiple of 10 times the frequency, it will go 20 dB less. What does that mean? So I can ask you, when does your amplifier provide unity gain to the input signal? I don't know, you tell me. Minus 20 what? So this is 10 to the 6 radian per second, right? And this is, here at DC gain is 40 dB, right? I'm saying, when will the circuit be providing unity gain or applying unity gain to the input? Unity gain meaning 20 log 100, that's equal to 0 dB, right? So in other words, I'm saying, when will your gain be 0 dB? Huh?
From this graph,
For your circuit, for the circuit that we analyzed, the circuit that we analyzed had a DC gain of 40 dB, right? Had a corner frequency of 10 to the 6. Okay? This means what? This means that at DC, V output over V input was equal to 100. In dB, it was 20 log 100, which was equal to 40 dB. Right? This is your circuit. This is the circuit that we analyzed today. Right? This circuit provided this data. At DC, I have 40 dB gain. Meaning, if I put a signal of 1 volt, peak to peak, what am I going to get at the output? Signal of what value peak to peak? In time domain. Come on. Gain, guys, gain. I have a signal that has a value, peak to peak value 1 volt.
Shouldn't we make it RMS?
No, I don't need to make it RMS. Has a peak to peak value of 1 volt. Right? If I pass it through this circuit at this frequency. This frequency is what? This is F naught. I'm 0.2 times F naught. Right? I'm passing it at this frequency. This signal has a frequency of 0.2 times F naught. Meaning what? Meaning that the voltage gain is going to correspond to 40 dB. It's still 40 dB here. It's flat gain here in this section. Right? So my voltage gain for this signal will be 40 dB. 40 dB corresponds to 100 in normal units, not dB. Right? So this signal looks like this. So what will the output signal look like? Forget about its phase, only the magnitude.
Would it be 100 volts?
Exactly. It's 100 volts peak to peak. The voltage gain of the circuit is 100. So you put in 1 volt peak to peak, you will get 100 volts peak to peak. This circuit will do that.
What did you say, 0 dB?
It will do that at this frequency, which is F naught divided by, or multiplied by 0.2, for example. Right? Now, I'm asking you, when will the output signal look like the input signal? The input signal is 1 volt. Exactly. Where is this 0 dB going to happen? That's my question. When? At what frequency will this 0 dB happen? Remember, this is 40 dB. And then what's going to happen here? The gain will decrease. I will be losing gain. I'll keep losing gain. How fast am I losing gain? I'm losing gain at 20 dB per decade. Every decade, meaning multiple of 10 times the frequency, I'm losing 20 dB of gain. My gain at DC is 40. So how fast, when do I lose 40 dB of gain? After 2 decades. Right? Not 2 decades in like 20 years. 2 decades is like 2 decades of frequency. Is this clear or not?
Decades means 1 and 10?
No. From 1 to 10 is 1 decade.
Okay.
From 10 to 100,
100 or 20?
100.
But
Multiply by 10.
Isn't it from 1 to 10 it was 37? So
No. 37, I lost 3 dB from DC to my corner frequency. So now let's, maybe you're being, okay, so I understand. So assume that so remember, okay, so this is the exact curve. I agree, maybe there's a little bit of confusion. So this is the exact curve, this blue one. If I want to approximate it, I can approximate it using this red curve. You agree?
Yeah.
So you can sort of neglect this 3 dB loss for now and answer my other question. My other question is, when do you lose, when is the output going to look like the input? At 0 dB, right? When is 0 dB going to happen? Here is 40. All the way until where? All the way until here. Fine, this is really 37, but assume it's 40. So until F equals F naught, my gain is 40, meaning my signal will be amplified 100 times. When will my signal not be amplified at all? When will I have a unity gain? It will be when I lose my 40 dB, when this 40 dB becomes 0. How do I lose this 40 dB? I lose this 40 dB because of this curve. the slope of this curve is always going to be minus 20 dB per decade. We will always be losing 20 dB every decade of frequency, which means that at f naught, I have full magnitude or full gain. At f naught times 10, I lose what? 20 dB. I lose 20 dB, meaning my signal will go from 40 dB gain to 20 dB gain. It can go from 50 dB to 30. It can go from 90 dB to 70. Whatever your DC gain, it will go down by 20 dB every decade. Okay? So I lost 10, I moved from 40 to 20 at what frequency? F naught times 10, or omega naught times 10. Right? And I moved from 20 down to 0 dB at F naught times 100. Right? So 10 times 10. So at F naught or omega naught times 100, my gain became 0 in dB. Meaning what? Meaning my signal that came in looks exactly like the signal that came out, in magnitude only, okay? Forget about phase. Phase, we did not look at the plot for phase yet. But in magnitude, that's what happened. We agree? Okay. In phase, if I ask you at that phase, okay, if I ask you what is the phase at DC, fine, you have to go look at the expression for phase of the signal, right? So you would put whatever frequency that signal is at. So for example, the sensor has an input frequency of whatever, 10 squared in radians, a radian per second, and your natural frequency or your corner frequency is 10 to the 6 in this case that we calculated. So you will have to calculate this and tell me what the phase difference is between your input and output in that case. Okay? So if I tell you what is the phase of the signal at when you have 0 dB gain, then you would have to go take your omega naught. So what then? Omega will be what? Omega will be 100 omega naught. So it's inverse tan minus inverse tan 100 will be the phase in that case. Because we said that I will have to calculate the phase, I will plug in the frequency and divide it by omega naught, which is the corner frequency of the circuit. So we said that I have a DC gain of 40 dB up to my corner frequency. And then my question was, at what is the phase when the signal at the input looks like the signal at the output? Signal input looks like a signal at the output, meaning I have unity gain. And we said that happens after 2 decades, meaning at F naught or omega naught multiplied by 10 multiplied by 10, so multiplied by 100. So at omega equals 100 omega naught, I have a gain of unity. So what is the phase at that? You remember, we have to plot gain and phase of the circuit, of the signal. So what is the phase of the circuit of the signal at that time? It's 100 omega naught over omega naught. So omega naughts cancel, so it's minus inverse tan 100. Okay? Mariam. So what are we going to do in Ramadan? So, okay. So what's next? The next thing they asked for is, okay, so we found F naught, and then here, this is this 100 that we talked about. So since the gain falls at minus 20 dB per decade, starting at omega naught, the gain will reach 0 dB in 2 decades, so it's a factor of 100. This is what we were talking about. Okay, so F naught, the corner frequency was 159.2 kilohertz. Multiplied by 100, then the gain, the frequency at which the gain becomes unity, or 0 dB, is 10 to the 8 instead of 10 to the 6, or 15.92 megahertz. So this multiplied by 100. Okay, that's this. Now what are they asking for? Now they're asking for what I was saying. Okay, you have a signal. These signals, they gave you a few different signals. These signals are 0.1 sine 10 squared t. 0.1 sine 10 to the 50. Remember, omega naught was what? Our corner frequency was 10 to the 6. Omega naught, our corner frequency here was 10 to the 6 radian per second. So what's going to happen below omega naught from a magnitude perspective? Nothing. The signal, the signal will be applied, the DC gain will be applied to the signal. Below omega is equal to omega naught. Above omega equals omega naught, I will start attenuating. How much attenuation will depend on how far I am from my corner frequency. Okay, so they're asking. So obviously, these signals with omega squared, omega naught equal with omega equals 10 squared. This is less than omega naught. With omega equals 10 to the 5th, this is less than omega naught. With omega is 10 to the 6th, this is exactly at omega naught. So I expect my gain of this signal to be 3 dB less than the gain at DC, or the gain below the corner frequency, right? So these two, probably the gain of the signal will be the DC gain. So it will be 100 in decimals, or it will be 40 dB in dB. 40 dB in decibels there. And then these two, one is at the corner frequency and one is higher than the corner frequency. One is higher than the corner frequency with what? Corner frequency is 10 to the 6. 10 to the 6 times 10 is 10 to the 7. 10 to the 7th times 10 is 10 to the 8th. So I expect that this will have, this I lost my 40 dB completely, right? I went 2 decades above. So I lost, this will be the unity gain response. It will have a unity gain response to this signal, right? So that's what they do in solving this example. So they take each one of these signals. So they take, so one has omega squared equals, omega is equals 10 squared. So then they find what? They find the magnitude and the phase, right? So you can find that from the plot, like we just did by plot, or by substituting in the equation. So the equation was 100. This is my DC gain. This is the k over 1 plus s over omega naught equation that we have. You can go substitute here and find the magnitude and the phase and do the math. Or if you like the plots and stuff that we did before, understand the concept of DC gain and corner frequency and stuff like that, you can actually do it without even applying the math. Because we know that, from the body plot, we suggest that, since this is 10 squared, less than omega naught, then the plot suggests that the gain will equal the DC gain. So the gain will be 100 in decimals or 40 dB. This is what the plot would suggest. And the phase would suggest that, if you go to the phase, here, the phase would suggest that at 10 squared, so at a small value of frequency, at a small value of frequency, so 10 squared over 10 to the 6 is what? 10 to the minus 4. So at 10 to the minus 4 f naught, meaning 0.0001, so you actually go here. So this is 0.1 omega naught. This is omega over omega naught equals 0.1. So at omega is equals over omega naught equals 0.0001. That's 10 to the minus 4. Right? So where is that? It's occurring here somewhere. What is the phase? What is the phase of the output signal? This is 0, minus 45, minus 90. What is the phase here? 0. Somewhere back here is, fine. This is getting to 0. Approximately 0. Yes, ma'am.
If we solve it using the graphical method,
Yeah,
and the
it will be
numbers are
approximate.
not-
It
yeah,
will be approximate, yes.
It's okay.
Exactly, yeah. I don't have a problem with that. As long as you show me that you tell me I solved it graphically this way, approximately this is like that, approximately this is like that, I'm fine.
So we don't have to plug in numbers.
You don't have to. But you have to do it that way, you have to know things. You have to understand what corner frequency is. You have to understand that, okay, I need to take omega over omega naught. It's here, 10 to the 10 squared over 10 to the 6 means 10 to the minus 4, means omega over omega naught is 0.0001. Then you have to, okay, then you go back, go to this curve, and you go all to the left and put a line here and tell me, okay, phase is almost 0. Right? Yeah, I don't have a problem. I can do it this way or that way. And the textbook says that. You can do it this way or that way. But that's why these curves are nice. If you understand these curves, and what they mean, then khalas, you don't need to substitute numbers and stuff like that. And you don't need to derive these transfer functions because, okay, you go to the capacitor, see what the parallel resistances are across the capacitor, you have your time constant. You have your time constant means you have omega naught. You put everything, you open up your capacitors and find your DC gain, then you have your K. That's it, you're done. You don't need to include impedances and complex numbers and stuff like that. It's easy, but you have to understand. Okay, so then they give you three more signals to apply the same thing to. But let's look at the last one, for example. The last one, we know it's the omega is greater than the corner frequency. So 10 to the 8th, which is what? Which is 100 times omega naught, right? 10 to the 8th is 10 times 10 of the corner frequency. So it's 100. What happened at that point? We know that we lost 40 dB. So which means that what the Bode plot suggests that the gain will be 1. It will not be 100 anymore. It was 100 here. We lost all the gain because we are 20 dB with 2 decades more. So the gain is 1 in decimals or 0 in dB. So there's no gain in that case. And the phase shift, you go back to the phase shift plot and you see, okay, what happens at, this is 1, this is 10, what happens at 100 omega over naught equals 100. I went to minus 90. That's my phase. Okay, so that's what happened to the signal from the input. So this is the sensor signal that passed through this amplifier. You were able to qualify what happened to the sensor signal, assuming the signal is low frequency all the way to some high frequency. Okay, so that's what you need to do because you will have sensors that provide signals. These signals need to go to the amplifier. How is this amplifier going to behave? You want to make sure that the circuit following the amplifier, which is maybe the speaker, is gonna, you're gonna be able to power up the speaker. For you to be able to power up the speaker, you need a certain voltage gain, and you need a certain power gain, for example, right? So, and you want to make sure that, for example, let's say in a speaker case, I don't think the phase shift is very important. I mean, I don't think somebody will recognize, or audio signals are around 20 kilohertz. If there's a phase shift, 1 over 20 kilohertz is what? It's a very small amount of time. So, if Abdulaziz is singing, for example, and I'm sampling that at 20 or 40 kilohertz, then my samples are very close to each other. Fine. If there is a phase shift between the input sample and the output sample of 90 degrees, that's what? 90 degrees is one fourth of 360, right? Yeah, it's 1/4 of this 360. So there's my sampling period is 20 kilohertz. So 1 over 20 kilohertz is the time between samples. And I'm saying that, okay, because of my amplifier, there was a delay in the signal. So the output signal is delayed from the input by 90 degrees. 90 degrees is 1/4 of my period now, the full period. So really, is somebody going to recognize, okay, Aziz is singing, and somebody going to recognize that there's a delay in the output from the speaker? Not really, not really. But if it's data, if it's data on the internet or image data that you're transmitting, and there's a delay, and you may be able to recognize that. I mean, there are things that you cannot recognize, like audio speaking, for example, unless the delay is very long, right? There may be things that are very critical, like the power system fault analysis, when you want to make sure that all the samples are exactly synchronized. Because if you don't do that, then maybe the circuit breaker opened before that one, but because you have delays and phase shifts, you don't really know what's happening, right? So in certain cases, it's important to know to make sure that all the signals, for example, are delayed the same way. If all the signals are delayed the same way in a power system analysis problem, then it's okay. Then they're all delayed the same way, they will not have a problem. But if some signal is delayed one way, other signals are delayed another way because of a different power amplifier circuit, then there's a problem. They're not synchronized, and you're not going to be able to tell me the proper root cause, assuming you're down to that critical situation where this root cause depends on that time delay. Right? So there will be applications that this time delay will be important, or the phase will be important. There will be applications where it's not very important yet. Okay?
Like here,
Yes.
it's 100 omega naught, right?
At 100 omega naught, the phase shift was minus 90 degrees.
Why is it minus 90?
Why is it minus 90 here? We calculate the phase. I mean, remember, for the simple RC circuit, it was 1 over 1 plus RC, 1 plus J omega RC. So the angle of the number below was 90, for example, or was 85, or whatever. I had to bring that to the top, so it comes up with a minus sign. Right? So there will be a minus 90 degrees phase shift between the signals. Yeah. So the signal will actually be leading.
We can use the minus tan.
Yeah, you can use the inverse tan. Yes, you can use the inverse tan. But and that's what I said in the example. You can either look at the curve, or use the table, or after you've calculated your transfer function, like we have here. Right? After you've calculated your transfer function, just substitute with, substitute with the frequency, you know, in this 10 squared for the first signal, 10 to the 5th for the second signal, 10 to the 6th for the third signal, 10 to the 8th for the fourth signal. Just substitute with omega is equal to 10 squared, 10 to the 5th. And then find, this is a number. These are two numbers on top of each other. First, the top one is real, the bottom one is a complex number. Find the magnitude of this fraction. And then find the phase angle of this fraction. It's a number. And then you will find that it's going to be 90, minus 90, almost minus 90. It's not going to be exactly minus 90. Right? If you just take it from the curve, it's going to be an approximation. Maybe minus 88. But you just tell me, okay, I took it from the curve. So see here, they say the body plot suggests that phi is equal to minus 90. But when you do the calculation, it's minus 89.4. Right? When you do the proper substitution, it's minus 89, which is okay. So it's, I mean, as long as you tell me, okay, I did it this way or that way. Okay? Yes, ma'am.
You said we will have a formula sheet.
Yes.
Where is the formula sheet? So we
It's
can
with Wissam, but I will have it. I asked him to send it to me to upload it today to the website. So I will try to. I will make sure that he didn't send it to me. I will. If you see him, remind him to send it to me. But I will also do the same, and I will upload it today to the website, because we have formula sheets for you to use, and it's good to use them to solve your homework so that you know how to use them on the
Use them
exam,
also on the quiz, right?
on the quiz, on the exam, anything. Yes, exactly. So yes, good point. And that's the end of the material we want to cover in chapter. I think we covered last time this DC coupled, capacitor coupled versus DC coupled. Why is this important? Because the next chapter is op amps, which we will, as I was hoping to start today. Op amps are all DC coupled devices. Why? Because capacitor coupled devices, meaning, you know, a configuration where you have an amplifier followed by an amplifier with a capacitor coupling between them, means that you have to actually construct this capacitor on the chip. For you to construct the capacitor on the chip, it requires space. And for you to actually be able to, you know, allow AC signals to pass through, 1 over SC or 1 over J omega C is the impedance of the capacitor, right? For you to pass as much AC content as possible, meaning anything beyond DC, I want to pass. For you to do that, what does that require on the capacitor? What size capacitor would I require? Small or big? Why? I want to pass. So 1 over SC is the impedance of the capacitor, right? Or 1 over J omega C, right? This impedance, if I have DC, if omega is 0, what's the impedance?
Omega is zero.
Infinite.
Oh, zero.
1 over 0 is very large, infinite. And if I have,
Very high,
if omega is a very, very large number,
then it's zero.
then it's the impedance is
Zero.
0. So this is omega, and the impedance is 0, right? I said very, very large number, right? But what if omega is a small number, like here? Omega is a small number, right? This is not this is frequency, or omega, right? Omega is a small number, right? For omega is a small number, what's going to happen to this? Not 0. The omega is not 0. It's a small number.
Approaches.
It will be attenuated. If I don't want to, right? If it's a small number, if it's a small number, what's going to happen to the impedance? I will have a big impedance, right? Big impedance means the signal will be attenuated. Large impedance because remember, this capacitor is in series with the signal, right? For the capacitor coupled amplifiers. So I will have a large impedance to the signal. So if I don't want to have a large impedance to the signal for low values of frequency, what can I do to this? I can make C what? If I make C huge, yes, exactly. If I make C huge, then any value of omega, even if it's small, will do what? Will pass through, will cause 1 over this to look large. This is going to be large because C is very large. So at 0, fine, it's like an open circuit still. But at 0.1, C is huge, C is infinite. If C is infinite already, then the impedance will be 0 automatically. How does it affect this curve? It will make this fly up here, right? Very quickly. So that I will not be attenuating low frequency signals. So this requires large capacitors, right? So that's why, op amps, for example, are integrated circuits. These integrated circuits are chips. You want to make them as small as possible. For you to make a large capacitor, again, go back to your 322 where you were studying capacitors and how do you calculate the size of the capacitor. Size of the capacitor depends on the charge you have placed on the capacitor, right? So it's the amount of charge and the distance between the two plates. For you to have a large capacitor, you need to have a large distance between plates, a big, nice dielectric, and large plates, right? That's a large capacitor. Can you do that on a chip? You should not do that on a chip because you will have a chip that's this big and you cannot do that, right? That's why integrated circuits, like an op amp, integrated circuit amplifiers, like an op amp, are typically DC coupled or direct. This is called DC or direct coupled. Discrete circuits that you make, you can design as capacitively coupled because you can put a large capacitor outside on the board in discrete fashion, right? These have applications and these have applications, right? So the next chapter will be on direct coupled circuits, direct coupled amplifiers. One example of a direct coupled amplifier is the op amp. Okay, so we will stop here. Next time we start chapter 2. Good luck on the exam. Exams Tuesday, as we said.